So I'd like to talk about a very typical problem we see. It's a problem where we deal with having multiple high gain amplifiers and saying here, and then I'm building it into a feedback path. We use this all the time for a whole number of different circuits, and where we might have like two high gain amplifiers. That also allows me to do the differencing. One amplifier, their amplifier, and the differencing. Putting it all together. And you think to yourself, well, what should be the problem, right? I mean, because we often want high gain amplifiers, and the primary reason we do that with feedback is that usually there's something that we have precise about the feedback element, but we don't trust our circuits. We don't trust the precision of our transistors. We don't trust the precision of the other circuits we're working with. Now, if we have something to give us precision, like very precise programmability, most of those questions start to disappear, it turns out. But let's work with the situation where we have some uncertainties, and we're going to work with that. If you look at this sort of simple structure, what you can start working through the math here, and kind of show an equation for V out, which then allows you to kind of put the various transfer function components in to this transfer function. And you're like, oh, that's great, no problem. And then you think for a second further, and you go, there's a lot of gain here, because maybe those are both like 50 or 100 or 1,000. We'll go with some simple examples in a moment. But here's the thing, right? You start with those numbers, and that's pretty significant. Well, what's a good case? Well, imagine that I say that tau 1, so this is in the first stage, is going to be the product of the two gains times tau 2. So basically, this is going to be the product of the two gains slower than this element. And let's see what we would get. Well, the net effect is if I do that, then this whole system in feedback, which you'd want to have basically be a gain of 1, gives you a response that basically gives you something that gives you a Q of 1, a resonance of 1, a 45-degree phase margin, which is really good for step responses. But you should sort of step back and think for a second. You go, okay, hold on a second. I have these two amplifiers, one maybe with both of them with gain, and I have to slow things down that much, or I have to speed something up. But practically, really hard to speed something up beyond a certain point. And by the way, you could actually do something very similar with tau 2 and tau 1, swapping them, one being slow and fast. I'm just picking one to start from. And what you find is, well, what does that look like? Well, imagine that we have for H1, we have this particular transfer function starting at, say, gain of 50, and then just kind of keeps dropping with frequency, typical integration, first order response. The second one, also has a gain maybe now about, say, 200, but it breaks now at a much higher frequency. And these are now separated by a factor of 10,000, which is the gain of 50 and 200. And if you do that, then you actually do get this very nice sort of Q equals 1 response, which you can see from the Q right at the corner frequency, that's equal to 1. All of this is really good, except think about something for a moment. I've had to take this first amplifier and slow it down dramatically. Now, that could be good from an energy perspective, depending on how I set up biases, but usually that's not what I'm trying to do here. And usually I'm going to do something further to this that actually makes this problem even more complicated. And so this for example, I would have a hard time wanting to go really low bias current here, because that might have some other negative impacts over the whole wide bandwidth that I'm using for those lower currents. Again, you have to look at the whole question of noise and other kinds of performance of the system you're building. None of these are a given. And you might go, well, why would I care about this problem? Well, a practical thing is if you put these two things together, what you find is you have the classic two-stage op-amp circuit, which lots of people love to use. And of course, typically the way it's built is you build a reference where you have the same current source for the two stages. So basically you're going to ratio it based on the W over L of the transistors. Again, remember that I've got to get the corners to separate by a sizable amount. That's non-trivial, at least if I do this as a sort of raw structure is done. And so I have a lot I have to think about there. And it usually means I've got to slow down one stage or slow down the other. In practice, you often slow down this stage,
often with putting a very effectively making it look like you have a large capacitance across here. But still, what you're dealing with is you're losing a lot that you didn't necessarily think you were losing in the overall problem. And so it's really important to kind of get a good sense of this. The other thing to realize is that these two-stage amplifier op-amps are tricky to get right. There are some good expressions and good approaches. And many times people often go and use these designs because these are often the ones talked about in many of the textbooks, not realizing that they're talked about in the textbooks because they're the hard case. And they're an example of this particular hard problem, not because they're the optimal design or the easiest thing to design in a particular case. So be very, very aware of the issues and the problems that you run into with these kind of feedback structures that show up almost everywhere.